Bismillah ar-Rahman ar-Rahim. We will discuss flow. Fluid flow could be a gas or liquid, and we are correlating the quantity to time. This quantity could be volume or mass. You see, whenever I put a small dot on the Q, it means the flow, the cardiac output. So, in other words, we can explain it in such a state. It is a mass or a volume passing a point in unit time. We have in this slide 4 items. First of all, the laminar flow. As you can see, laminar flow in which the layers are steady and there is no eddies or swirls. And as we approach to the periphery, we find the flow reaches 0. And of course, the maximum is in the middle where it is doubled. And this is this figure on the right shows the correlation between the pressure and the fall and the flow, and we can see that it's linear. The relationship between both is the resistance. So if I want to estimate the resistance, I can create an apparatus such what is present in front of me, and where there is a constriction and there are pressure devices on other sides, the resistance is being calculated from the drop of pressure. You see, of course, there are factors that affect the laminar flow, and this equation is called Hagen-Boisé equation. Of course, we have something or many things on the numerator and some things in the denominator. As we can see, it's we have a constant. This constant is pi over 128. We sometimes use 8 instead of 128 whenever I use the radius, not the diameter. So in the upper or the numerator, we find what we call the difference in pressure and the diameter to the power of 4, as we can see. On the denominator, we can see what is called the eta. It looks like an N, but we prolong this part downwards slightly, and the length. All this creates the laminar equation. Of course, we can ask any colleague how can you get benefit out of this equation. We can of course use it in cases of shock. Of course, you must apply to a wide bore cannula, because the increase in the diameter increases the flow 16 times. So this is the most important item. Of course, whenever we intubate the patient, we must select the proper size tube. On the other hand, the turbulent flow, the fluid is going in a turbulence way. It swirls, and it creates a relationship between a pressure and flow in some sort of a non-linear relationship. So in case if we want to increase the flow correlated to the pressure, we must much increase the pressure to gain a proper flow. The factors affecting the turbulent flow, as we can see, it is proportional to the square root of pressure difference, inversely proportional to the square root of length, and inversely proportional to the density, which is called rho. You can write it as if you are writing a P from downwards upwards. You make a turn upwards. You see, of course, the behavior of the turbulence makes it difficult to create an equation to make a simple formula. You see, now we come to discuss what we call the onset of turbulent flow. We must remind this equation, Reynolds number, in which it is formed from the linear velocity times rho, which the density, times the distance, or the diameter, I'm sorry, over eta, which is the viscosity. Of course, viscosity is resistance between the layers of, or the friction forces between the layers of the fluid. If Reynolds number exceeds 2000, we call the flow turbulent. You see? So in other words, if I fix the distance, or I'm sorry, the diameter and the density, I can see that the Reynolds number will be correlated to the velocity. You see? Turbulent is always present in orifices and in bends. You see? And whenever I have helium, it can decrease the density, which is present in the numerator. So we can improve the flow by inducing helium to increase the oxygenation of a patient who is suffering of respiratory problems. Clinical aspects of flow, it's based, as we said before, on the velocity. You see, we have a curve on the left showing the relationship between the size of the airways, whether it is an endotracheal tube or a scavenging system, and the flow in liters in minute. And we can correlate the relationship between from the following items. Whenever I have a typical anesthetic mixture of 60% nitrous oxide and oxygen with a temperature of 20, we find that the critical velocity is less than that of using air. You see, means that there is more possibility of turbulence using the mixture than in air. On the other hand, if we use humidified gases with a temperature of 37 with carbon dioxide, also the critical velocity will be changed, and these two items will raise the critical flow. In other words, I can increase the flow in such circumstances before reaching the Reynolds number. Also, the correlation of the size of the tubing system and the flow is quite noticed. Whenever I have a tube of 9 millimeters, if I apply a flow of 9 liter per minute, not more, I can create a laminar flow. And of course, we know the 22 millimeter size of the tube of the breathing systems we have. This also, if we pass a flow of more than 22 liters per minute, will create a turbulent flow. Of course, turbulent flow is present in the low respiratory ways, though they are less in diameter because the flow is going slow, and of course in quiet breathing and slight talking, not in coughing and speaking, the flow is always laminar. Of course, if the endotracheal tubes or the passes of the airway contain any mucus, of course it will affect the flow. Lastly, if we have a peak flow rate of more than 50 liters per minute, what's the meaning of peak flow rate? It is the maximum flow that I can required in any situation of under anesthesia. In other words, as we know, the reservoir bag in the Med.S system is a bag to preserve this peak flow, so that the patient, whenever he is in need of such 50 liters per minute, he can find it easily. This is what we call the peak flow rate. Of course, in such a large rate of the flow, of course, will be turbulent. The fifth item is the tension. First of all, the problem of the diameter of the airways or the vascular nature doesn't depend upon only the diameter, but there are many other things controlling the flow. Tension, of course, we know that the blood vessels and are not blood vessels and the bronchi are not rigid, so they are malleable. They have a variable radius. We have what we call the Laplace law. Laplace law is being confined whether to a cylinder, as you can see on the figure, or on a sphere. You see, the sphere has two planes of curvature. This is why this makes the difference between the equation both types. As we know that from the previous chapter, but that Laplace law correlates the pressure to the tension over the radius. This equation is confined to the cylinder. As far as the orifices like the alveoli, we multiply 2 by the tension to create Laplace law in a sphere. Of course, whenever to preserve this pressure acting on the wall of the blood vessel by the fluid, we must have a balance between the pressure and the elastic and the muscle coat of the blood vessel to maintain the pressure. Of course, the correlation, sometimes it has been embarrassed, and sometimes the blood vessel pressure cannot tolerate, so that we have what we call the critical closing pressure, where the pressure is much decreased up to that the muscle coat and the elastic tissue cannot yield to keep the blood vessel patent, and of course the blood vessel can be shut off. On the other hand, whenever I apply this equation to a sphere like the alveoli, we can say that whenever the alveoli is being distended, of course, it will be it will affect the smaller ones. You see, so you must have something to control this over expansion or over a collapse. This is the function of the surfactants. So this surfactant makes the surface tension variable, whether it increases its concentration or decreases it to preserve the pressure within the alveoli so that it will not collapse, to maintain the tension and the radius in a proper correlation. Viscosity, as we said before, it is the friction between the layers of the fluid. You see, of course, if the hemoglobin or the fibrinogen is increased, the viscosity will increase, of course, and will decrease the blood flow. Of course, we have circumstances where the viscosity has been increased in old age and in low temperature and smoking patient, while treatment with low molecular weight reduces the viscosity. The Viscometer, as you can see, it's made of a cone. This cone, we put the fluid where we want to measure its viscosity, and we have a maintenance of temperature. We have a maintenance at temperature, and then this cone is being dragged by a torque. This dragging function gives a hint about the viscosity of the liquid. This is how we can measure its viscosity, as you can see by a light. This light is being hit on a mirror, and the mirror will reflect it on a dial where it can measure the viscosity. On the other hand, we can, of course, notice from the descent of any fluid its viscosity by measuring by a photocells. Of course, this photocell will give us a hint about the rate of descent of the fluid, and hence on viscosity. Flows through a Venturi. Venturi is some sort of a double laminar flow attitude, where we have a tube where it becomes constricted, and then it begins to be rearranged again to reach the final diameter that it was present before. And we can see there is the difference of pressure between the different sides. At this constriction, we have a fluid going through. This fluid has two types of energy. We have what we call the potential energy, which is responsible. P is responsible for pressure, and we have what we call the kinetic energy, which is responsible of velocity. So as we can see, the decrease in the pressure at this constriction is after what the discovery of Overt, which was called Bernoulli. So Bernoulli who discovered the low pressure at this constriction. Of course, to avoid much loss of heat energy from the friction, the inclination must be gradual. You see, what are the clinical application of the Venturi, which is a famous question? We have what we call an injector, as we can see, a Venturi, and there is a tubing system at this constriction where entrainment occurs. Entrainment means that I'm sucking something from a container. This is the principle of the injector. This is the second thing is the nebulizer. As you can see, this is the injector where I can suck. It used to be used in the past as a suction apparatus by the flow of water. And this is the nebulizer, as we said before, where there is a container. This container, the liquid is being sucked, and then it hits what we call an ancial. This ancial breaks down the droplets of the liquid to very fine molecules where the patient can nebulize. The first application of Venturi is what we call the Venturi Mask. As you can see, a patient, he is inspiring oxygen with the flow of 1 liter, where this tubing system is ended by a constriction. So if we apply the Bernoulli effect or Venturi apparatus effect at this constriction, we find that the velocity increase. This will suck more air, and we can increase the flow. Instead of 1 liter of oxygen going through, it will pick up 9 liters of air from the surrounding. On the other hand, the friction of the oxygen molecules at this site entrains more or gets more air from outside. This makes what we call the entrainment ratio, which is the flow of 1 oxygen to the 9 liter of oxygen of air. I'm sorry, being taken by the 1 liter of oxygen. The Quanda effect, as we can see, it is a Venturi effect, but instead of ending by one opening, we can make it branched, as we can see, into two branches. You see, so you may say the flow will be divided on both sides. No, it's not divided, but as a matter of fact, it goes out. It clings on one of the walls, whether the upwards or the downwards. You see, this is what we call the Quanda effect. If we apply at this narrowing part, where of course, as we said before, the velocity is increased and the pressure, a tubing system, we can direct the flow through this Quanda, whether upwards or downwards, as if we are using valves. So this is what we call the fluid logic that is used in some special ventilators where we don't have moving parts, and it acts as a switch. So this is the benefit of the Quanda effect, and it explains why whenever I have a constriction, whether in the coronaries or in the upper airway, where this constriction area is being divided into two branches, one of the branches induces an infarction, and on the other branches does not induce an infarction, because according to Quanda, the blood will be passed through one branch, leaving the other branch. So this is a hint about fluid flow. So I hope that I succeeded. Wassalamu alaikum wa rahmatullah wa barakatuh.